Today we'll be going over weak-base dissociation, known as KB, and acid-base properties of salt solutions. Just like in 18.5 acid dissociation, weak-base dissociation in water is similar. So we're going to have our base in aqueous plus water as a pure liquid going into a acid in aqueous solution, hydroxide in aqueous. Just like we did with the acid dissociation, we're going to form the constant. The constant is Kb, referring to the base, all over the products, so it'll be the acid all over the hydroxide, all over the base. This Kb refers to base dissociation constant. When the Kb increases, so does the base strength. A strong base, the reaction goes to completion. That means Kb is greater than 10 to the third. While a weak base, the reaction does not go to completion, so the Kb is less than 10 to the third. Let's write out a base dissociation constant. Given ethylamine going to water, we form HO, NH3 plus OH minus. So let's write this out as a base dissociation constant. First thing we need to do is identify how many carbons we have and to write the simple structure. So we know we have 2 carbons, so C2. We have 1, 2, 3, 4, 5, 6, 7 hydrogens, a nitrogen, and an oxygen. Now, a better way to write this to show the alcohol and the amine group is to write it as HO, CH2, CH2, and H2 plus water. Goes to, again, the little bumps are the carbon. We have 2 hydrogens. And we're going to just simplify it like we did previously. So HO, CH2, CH2, NH3 positive, plus hydroxide, OH minus. Now the Kb is going to equal to the acid, the HO, CH2, CH2, NH3 plus, the hydroxide, OH minus, all over the acid, HO, CH2, CH2, NH2. Remember, we do not add the water because it is a pure liquid. And if you were curious, we get a Kb of 3.2 times 10 to the minus fifth. So because it's less than 10 to the third, this means it's a weak base. Now, let's look at an example. So if I was given what is the pH of a 0.15 molar ethylamine solution, and we know from what I just did the Kb is equal to 3.2 times 10 to the minus fifth. Well, if you remember when we did the Ka's, if we have the molarity of the base and the constant of the base, we can find pH. So the first thing we need to do is to write the dissociation equation and Kb expression, which we already did. So I'm just going to show this again. So here it is again. We have the dissociation equation and the Kb expression. And again, we know the Kb is equal to 3.2 times 10 to the minus fifth. Alright, so the next thing we're going to do, just like we did with the Ka, we're going to set up a reaction table. So that's what we're going to do next. Alright, so the first thing we're going to know is that X is going to equal our base of dissociation, which is going to equal our acid, which is going to equal our hydroxide from our base. Alright, so our initial, what we had was 0.15 molar. We know our water doesn't have an initial, nor does it change, nor nothing happens in the equilibrium. While our initial for hydroxide is 0, and our initial of the acid is 0. Now what changes is we're going to dissolve our base, we're going to get hydroxide, and we're going to get our acid. So we're just going to bring this down. Alright, then the next thing we're going to do is we're going to make an assumption. So our assumption is that the HO, CH2, CH2, NH2 is a weak base. Now, we actually really know this because it had a Kb that was less than 10 to the third. So we know for sure this is a weak base. So because it's a weak base, we can state that the HO, CH2, CH2, NH2, instead of being equal to 0.15 minus X, we can assume it's going to be 0.15. Alright, so the next thing we're going to do is we're going to now substitute our values. So we know we have a Kb is equal to the hydroxide, our acid, which was also X, and because we stated our base is a weak base, it's 0.15. So we know our Kb is equal to 3.2 times 10 to the minus 5, and we end up with X squared is equal to 4.8 times 10 to the minus 6. Our X is equal to 2.2 times 10 to the minus third molar. And if you wonder what I did, I just took the square root of both right here. And I multiplied 0.15 to 3.2 to get us that 4.8. So now that we have X, remember X was equal to hydroxide. So we know hydroxide is equal to 2.2 times 10 to the minus third molar. Now because we're looking for pH and we have hydroxide, well, we can first find pOH. So the pOH is equal to the negative log of hydroxide, which is equal to, when we plug this in, 2.66. Remember our sig figs. Because we started with 0.15, that was two significant figures, so I kept it with our molarity. And with our pH, we showed those sig figs after the decimal point. Now for the pH, so we know that pH is equal to 14 minus the pOH. and we get 11.34 as our answer. So just like our Ka, it's the same process as our Kb. Now for a little bit of a flow chart. So we can go from pH to pOH by using pH plus pOH is equal to 14. pH to hydronium is 10 to the minus pH, or from hydronium to the pH is negative log of that hydronium. Now, from the molarity of our acid, we can use the Ka to find the weak acid, or we can find the strong acid, because the hydronium is associated normally with the strong acid. Just like with pOH to OH, we're going to use now 10 to the minus pOH, and for the hydroxide to the pOH, we can use negative log of the hydroxide. Now, if we want to look for the weak base, we're going to use the Kb. If we're looking for the strong base, it's associated with the hydroxide. So let's learn a little bit of some shortcuts. So we know that our weak base, the association equation, and the Kb expression, well, since we know we're working with a weak base, we can just assume that x squared, which is our acid and our base, and our B initial minus x, we can assume it's actually just x squared all over the B initial if it's a weak base. That means, also don't forget that our x represents our hydroxide as well. For the weak acids, we have our dissociation equation and we have our Ka expression. Just like the weak base, we know that we get x squared all over our HA initial minus x, but we can assume, since it is a weak acid, that it's going to give us a Ka is equal to x squared all over that HA initial, as long as we know it's a weak acid. Now, just like with the weak base, this time our x is going to also help us represent our hydronium, H3O+. So this really helps us go from pH, pOH, Ka to Kb just by knowing this information. Alright, so let's take a look at another problem. Alright, so given the pH of a 0.15 molar aqueous solution of HClO is 4.18, what is the Ka of HClO? Alright, the first thing I need to do is first identify, is this an acid or a base? Well, because it has a pH that is less than 7, that means it's an acid. Second, is this weak or strong? Well, I know what my strong acids are. They are HCl, HBr, HI, so hydrochloric, hydrobromic, hydroiodic, sulfuric acid, nitric acid, and perchlorate. So since it's not one of these 6, I know that this has to be a weak acid. So I can use my assumption. So I don't need to draw out the reaction table. So I can save myself a little bit of time. Alright, so first thing we're going to do is we're going to set up the acid dissociation and the Ka expression. Alright, so I have HClO aqueous mixed with water. Now, because I know that this is my weak acid, I need to form a weak base. So that's going to give me ClO negative aqueous. And because my water was my base in this, I need to form hydronium, which is the conjugate acid of water. Next thing I need to do is I need to set up the Ka expression. So Ka is equal to ClO negative H3O plus all over HClO. And remember again, water is a pure liquid, so it does not count. So again, instead of drawing out the reaction table, I'm going to do my shortcut, so x squared all over 0.15. Again, I know this is going to be 0.15 because this is a weak acid. Now, I'm going to take a look at what I have. So I have molarity and I have pH. What I don't have is Ka. So I need to find out what is the hydronium in water and if I can use that. So what I'm going to do is I'm going to take H3O plus is equal to 10 to the root minus pH, and I'm going to use that pH. So it gives me 4.18, and because remember it's 2 sig figs after the decimal, I'm going to have 2 sig figs for my molarity, and I get 6.6 times 10 to the minus 5th molarity. So that's going to represent my hydronium as well as my base. So now I'm just going to plug in those numbers. So I'm going to take Ka is equal to 6.6 times 10 to the minus 5th. I'm going to square that because I have two of the same numbers all over 0.15. And I get 2.9 times 10 to the minus 8 as my answer, molarity. So again, it needs to be 2 sig figs because I have 2 sig figs after the decimal point for my pH. Now I'm just going to make sure my assumption of getting rid of that minus x for the initial of acid is true. So I'm going to take that molarity I got of Ka, 6.6 times 10 to the minus 5th, and I'm going to divide it by that molarity that I started with, and I'm going to get, times it by 100, is equal to 0.044%. So that is definitely less than 5%. So again, this was a valid assumption. So usually anytime you have a weak acid, weak base, you can make the assumption that the acid initial or the base initial will not need that minus x. But always double check to make sure it's verifiable. Alright, so the next topic we're going to talk about is section 18.7, acid-base properties of salt solutions. So we're going to start identifying what is an acid and what is the base of a salt. So if I was given NaCN at 0.1 molar, what is the pH? Well, is this NaCN a strong acid, a strong base, a weak acid, a weak base, or neutral? Well, we don't know. So we need to figure that out before we can start the problem. So what I have for you is this little flow chart. So this can be found on the Chem 201 website as well as a link in your course documents. Now this is to help you identify acids and bases, but you're going to need to know how to identify them without this flow chart. So this is great use for practice, but you need to start knowing which ones are which. So I'm going to break this down for you and you can understand it a little bit better. So let's get started. Alright, so let's look at acetic cations. First one, cations that are conjugate acids of a weak base are weak acids. So we should know this. A weak base will have a conjugate weak acid. So let's look at an example. If I have a base plus water goes into equilibrium, I have my acidic base plus my hydroxide. I know that if this base is a weak base, then that means this acid has to be a weak acid. Now we went over what our strong bases were, and our strong bases were those that were in group 1, group 2 with a hydroxide or with an oxygen at the end of it. The next acetic cation are those small, highly charged transition metals. Cations are weak acids. So for example, iron 3 plus would be a weak acid. Chromium 3 plus would be a weak acid. And aluminum 3 plus would be a weak acid. Now, how we normally see the iron and why it is a weak acid is we see iron mixed in with 6 waters with a 2 plus, and it actually forms the conjugate iron with 5 waters and 1 hydroxide. Now, what does this molecule actually look like? Some of you are wondering, so I'm just going to draw it for you. So because there are 6 things around the iron, we know that this is going to be an octahedral. So I'm going to draw out the octahedral. And then it's going to have the water all around. Just like that. Alright, let's get to the next step. Number 3, group 1 and group 2 cations are neutral because they are from strong bases. So for example, let's look at sodium hydroxide. So sodium plus water, we're going to get Na plus hydronium. So because sodium hydroxide is a strong base, that means its conjugate, the sodium, is going to be neutral. Alright, so let's take a look at anions. Just like we said for the cations, if we have an anion that are conjugate bases of a weak acid, they become weak bases. So again, a weak acid has a conjugate weak base. A weak base has a conjugate weak acid. Let's look at an example. We have HCN plus our water forms Cn plus hydronium. Now we know HCN is a weak acid because it's not one of the 6 strong acids, so that means its conjugate needs to be a weak base, which is the anion, Cn negative. Alright, so for polyprotic acids, they are amphiprotic. That means they act as either an weak acid or a weak base. So to determine the overall acidity of the solutions, we normally compare the magnitude of the Ka and the Kb. So let's actually see what a polyprotic acid is. So let's do carbonic acid. So we have H2CO3 plus water becomes HCO3 negative plus H3O plus. Now this can be broken down even more to HCO3 minus plus H2O becomes carbonate, CO3 2 minus, plus H3O plus. Now, because the carbonic acid lost a hydrogen in the product, we know that this is the acid, this is the base, this is the conjugate weak base, and this is the acid. Now we know that H2CO3 is weak because it's not one of these strong acids. Now let's look at the second reaction. So now we have HCO3 minus going to CO3 2 minus, the carbonate. So that means it loses a hydrogen, so that means this is the acid. Now, and this is the base, while this is the base, and this is the acid. So as you can see, HCO3 minus is a base here, but it's also an acid. So let's do an example. Alright, so let's get an Na2HPO4 plus water forms sodium plus HPO4 2 minus. Now I'm going to be looking at this reaction, HPO4 2 minus. So the first thing I'm going to do is I'm going to make it into an acid, and then I'm going to make it into a weak base. So here we go. So I have HPO4 2 minus. So if I'm going to plus water. So if I'm going to make it into a weak acid, I need to lose a hydrogen. So it becomes PO4 3 minus plus hydronium. Now I'm going to make it into a weak base, PO4 2 minus plus hydronium. Now it becomes H2PO4 minus plus OH minus. Now I want to figure out, well, is this HPO4 2 minus weak or stronger base, acid or base? Which one is it? Well, the first thing I'm going to do is I'm going to go to Appendix C in my book, and I'm going to find the Ka of HPO4 minus, and I get Ka of HPO4 minus is equal to 4.2 times 10 to the minus 13th. Now, I want to find the Kb. Well, to find the Kb of HPO4 minus, I need to take the Kw all over the acid of HPO4 minus. So if I'm looking here, this is the weak base, so this means this is the acid. I'm going to find the acid, H2PO4 minus, in Appendix C of my book, and I get 1.00 times 10 to the minus 14th all over 6.3 times 10 to the minus 8th, which gives me 1.6 times 10 to the minus 7th. So looking at the Ka and the Kb, I can see that my Kb is bigger than my Ka. So that means HPO4 2 minus is a stronger base than an acid. So that means Na2HPO4 is more likely basic. The next one is neutral anions. Conjugate bases of strong acids are neutral. So our conjugate bases of our strong acids are chlorine, negative, bromine, negative, iodine, negative, NO3 minus, which is nitrate, perchlorate, ClO4 minus, HSO4 minus. Now, warning, HSO4 minus is not a weak base, but is a weak acid. So the problem I did showing you the difference with Ka and Kb, this is why. So HSO4 minus has to be a weak base, not acid. So only 5 chlorine, bromine, iodine, nitrate, and perchlorate are going to be neutral.